All right, let's talk about chemistry. Now, I know a lot of people take biology, so they don't have to take a chemistry class. This is going to be friendly chemistry. This is the chemistry that is going to allow us to understand how living organisms can go through evolution and adaptation and energy processing and all of these things that we need to know. So, let's get into it. I promise it's nice chemistry, okay? So remember your chapter objectives. These are going to be what you are required to know from this particular chapter. When in doubt, please go read the sections on these in the book. But let's talk about elements, okay? All living organisms are composed of elements. You probably had to look at and learn parts of the periodic table of element at some point in your education. I had, I think, an 8th grade teacher who made us memorize the entire thing and then fill it in from memory. I'm not going to do that, okay? Here's what I need you to know about the periodic table of elements, okay? Elements cannot be broken down by any ordinary chemical means, okay? There are ways that scientists can absolutely split atoms and do different things like that. But our bodies are using these elements to make us what and who we are. Okay, so there are some big ones that we are going to be learning about in this particular unit, and that's going to come up again and again. The big one is carbon. Okay, we are carbon-based life forms, and so carbon is going to be making up a majority of the elements in our body. In the image here, you'll see, though, that oxygen actually makes up a lot more, as well as hydrogen. So carbon, hydrogen, and oxygen are the big three, okay? Those are going to be really important, and they're also going to be some of the ones that we see in red here. Hydrogen being the first element, carbon, nitrogen, oxygen, phosphorus, and sulfur. These elements are really important in building our cellular structures, providing us with energy, providing ourselves with the ability to reproduce and go through that whole reproduction part of the living characteristics of life. So when we talk about elements, we're talking about atoms, and we're talking about them in terms that our body is using. We actually do have a lot of different elements that we use that aren't going to be in that big kind of huge portion of our bodies, including things like trace elements, things like iodine. You need iodine for your thyroid to function appropriately. Things like iron. You need iron so that your blood cells can effectively move oxygen around your body. Well, obviously we need oxygen. It's the biggest part of the pie when we look at what is making up a human. And so when we talk about these elements, even though we're going to focus on a couple of them, keep in mind that your body is going to need a lot of these in order to function appropriately. And that's why, like, if you look on the side of a cereal box, it'll talk about all the different things that you're, getting from that food source, all the different vitamins, the elements, the magnesium, the sulfur, the things. That's why, is your body does actually need that stuff, okay? Now, when we look at elements, we generally interchange the word element and atom together, especially in biology. It really means the same thing for us, okay? So when you're looking at an atom, you are looking at the particular structure that is going to be used to build you as a human, okay? All of our atoms have a nucleus and then an outside section called orbitals where you will find electrons, okay? Electrons are negatively charged particles that are not found in the nucleus of the atom, and they are kind of in a cloud outside of that atom, okay? Inside of the nucleus of the atom, you will find protons and neutrons. Protons are going to have a positive charge, and neutrons are going to have a neutral charge. For our purposes in Bio 110, the things I really want you to think about are the protons and electrons, okay? When we look at an element such as helium, which is the example here, helium being element 2 on the periodic table of elements, we see an equal number of protons and electrons. Neutrons too, but neutrons don't have a charge. And so with what we're doing in our class, if you do chemistry, they're going to teach you a lot more than this, okay? We're focusing on what we need for biology here. Your protons are positive, and those positive charges have an equal number of electrons, which are negative. That means that this particular atom has an overall neutral charge. There's no charge here, okay? The two protons are going to neutralize the 2 electrons, and so my overall charge of this is 0. When we talk about charges, that's what we use when we're talking then about the way chemical bonds can form. So electrons can be arranged in an atom It looks like I'm going to have to fix a spelling mistake on this one. But electrons are arranged in shells, okay? The innermost shell can hold 2 electrons, and then the shells outside of that hold up to 8 electrons. When an atom is full of 8 electrons in its outermost shell, it has fulfilled the octet rule. It means that the atom is happy. Now, that doesn't mean that the atom doesn't have a charge, though, because if we look at something like carbon, okay, carbon has 2 electrons in its innermost valence shell here. Whoop. Go back. Okay, so we have 1 electron right here, 1 electron here, okay, and then we have 1, 2, 3, 4. Well, carbon is 6 on our periodic table of elements, which tells us that it has 6 protons and therefore 6 electrons, okay? When it has 6 electrons, that means its outermost shell is missing or can hold 4 more electrons. But if that carbon is holding 4 more electrons, then I am adding 4 negative charges. And so I'm basically going to make that atom slightly negative. Okay? Atoms can give up, accept, or share electrons to have 8. They don't really care if that's going to be a negative number. Really, the big goal there is to be fulfilled in having the outermost shell full of electrons. The more that you can fill that outermost shell, the more reactive that particular element tends to be. So when we look at something like hydrogen, hydrogen has 1 electron and it has 1 more it can hold because hydrogen is special. It can only hold 2. Hydrogen is going to interact with literally everything else because hydrogen just has 1 electron to share. It's like, okay, cool. Have this with me. What that ends up meaning is that when we're trying to fulfill the outermost shell, that electron shell of 8, that octet rule, we are going to see chemical bonds forming. So, an atom is going to have different kinds of chemical bonds that it could form. There are 2 types of generalized bonds. We have ionic bonds and covalent bonds. Now, when we talk about science, one of the big things is to make note of the words and what they mean. So attraction between opposite charges, something that is charged is called an ion, okay? So an ionic bond means that I have 2 charges, 2 or more ions or 2 or more charges, okay? Covalent means sharing electrons because valence refers to the electrons and co refers to sharing. If you cohabitate with someone, you're sharing a living space with them. If you are cooperating, you are sharing your time and effort and energy. And so when we look at these chemical bonds, we can have shared chemical bonds in the forms of nonpolar and polar covalent bonds, or we can have ionic bonds, okay? We're going to go through each of these in a little more detail. So, ionic bonds. I like to think of this as give an electron, take an electron, like give a penny, take a penny, okay? What happens here is we find some elements will have either have 1 extra electron in the outside shell or maybe be missing just 1 extra electron in the outside shell. Well, what ends up happening here is for sodium to fulfill its octet rule, it would have to get somehow by sharing or receiving 7 more electrons. That's a lot, okay? That's a lot of electrons for sodium to pick up. Or it can just get rid of 1. It can be like, I don't need this. This is extra, right? I don't need this. So what's going to happen is sodium is going to have this outside extra electron, and some atoms such as chlorine have 7 outside electrons. And so chlorine is going to just take this electron here, and now my sodium has fulfilled its octet rule, 1, 2, 3, 4, 5, 6, 7, 8. But now I have 1 more proton than electron. Okay, and then chlorine, the same sort of thing. It's fulfilled that 8, but now it has one more electron than proton. And so I start to see a slight negative charge with the chlorine and a slight positive charge with the sodium. And that is how salt forms. Salt forms in crystals because the sodium and the chloride are now attracted to one another. Okay, I like the give a penny, take a penny because in my mind, I go like, I don't want a penny in my pocket, but every once in a while, I might need a penny or a quarter or whatever, okay? You're giving something up to fulfill a requirement, but now I have a slight positive here because if I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, right? That means that I had 10 protons. That means I had a charge of 0. But now I have 9 electrons and I still have 10 protons, which means I have a charge of 1, which is why sodium is a little bit positive. And then chlorine is going to be opposite, where if it has 8, so 2 plus 8 is 10 plus 7 is 17, right? And 17 protons, it would be neutral. But now it has 18 electrons and 17 protons. And so I have a negative 1, which is why I end up seeing this slight positive and this slight negative here. Okay, that's going to be our electrons being kind of donated or received. Now, not all elements do this. And in fact, a lot of elements prefer to form covalent bonds. Okay, covalent bonds are going to be the sharing of electrons. And so you're not actually like giving up that electron, you're just sharing it. There are 2 kinds. You can have the polar covalent bond or the non-polar covalent bond. The thing here is if you see non in front of something, it means without or no. So non-polar, no charge. I have siblings. Okay, I feel like a lot of us have siblings. I have siblings, and I'm going to tell you right now, if I were splitting like candy with them and I unequally split those Skittles or M&Ms, there's going to be a charge situation when we're growing up, right? So polar covalent bonds is going to be an unequal sharing and it's going to result in a charge. What that generally means is one atom is much larger than the other. And so the protons in the larger atom, there's more of them, right? If this has 10 protons and this has 2 protons, which is not what the numbers are representing here. So we're just giving an arbitrary number. 10 is going to be bigger than 2, which means the electrons will get pulled closer to the nucleus of atom 2, okay? Or vice versa. We're going to see this unequal sharing where these electrons are just kind of pulling. It's like tug of war, right? You're going to have this uneven sharing where someone is stronger than the other. Non-polar covalent bonds, equal sharing, right? My mom, if she were splitting the Skittles between us, we would each get an equal number, and then whatever was left over, she got. That kept the peace, right? That's going to be an equal sharing of electrons. And a lot of times we see this between electrons that are the same. So something like oxygen, right? Neither oxygen is going to be bigger than the other. But then something like water, right? The oxygen is going to be much larger than the hydrogens. And so we're going to see charges in polar covalent bonds and no charges in non-polar covalent bonds. Okay? These different kinds of chemical bonds are a little bit like Legos in that you can kind of take them apart and rearrange them. And that's what brings us into this idea of chemical formulas and reactions, okay? So when we look at a chemical formula, we are looking at how things are rearranging between chemical bonds of different molecules, okay, or different compounds of these atoms that exist. So for instance, this is an equation for photosynthesis. If I have 6 CO2 and 6 H2O, okay, on the left side of the arrow, so I have the box around that, those are my reactants. I am going to combine carbon dioxide and water plus sunlight, and I am going to generate from that process products of glucose and oxygen. What's really cool about this, though, is when we look at these chemical bonds, we're rearranging them and we're not actually losing any of our carbons. Because if we go on this side, we have 6 carbons, okay? We have 12 hydrogens, and we have 2 times 6 is 12, and 6 times 1 is 6, so we have 18 oxygens, okay? So you imagine there's a 1 here, so 6 times 1 is 6, 6 times 2 is 12, and you imagine there's a 1 after this oxygen, so 6 times 2 is 12, 6 times 1 is 6, 12 plus 6 is 18, okay? On this side, in order for this to be what we see in nature and in chemistry, we would want a nice balanced equation. So if I should be able to count that there are 6 carbons, because again, we would put like a 1 in front of here. So there's 6 carbons, there are 12 hydrogens, right? And then I have 6, and then 6 times 2 is 12, 6 plus 12, 18 oxygens. So when we talk about how nutrients cycle, we're really talking about elements and how they can form different kinds of bonds, and those bonds can be broken and reformed, but we're not actually removing any of those things from that particular organism or chemical formula or reaction or equation. Okay? So check your understanding for chemical bonds and subatomic particles being those atoms, those those protons, electrons, and neutrons. And then if you don't know the answers to these, remember, rewatch the lecture, watch some of the videos that are posted in Canvas, or go and read the book. You should read the book, okay? Now let's move on to water. I mentioned that water is H2O. Right? H2O. What that means is we have an oxygen, which has 8 protons and 8 electrons, and then hydrogens, which each have 1 proton. Okay? Which means they also have 1 electron. Because remember, when we're looking at the base of these things, they are all balanced. Now, 8 is much larger than 1. So what we'll see is these hydrogens are going to form a relationship with this oxygen in that polar covalent bond, where that electron is pulled closer to the oxygen, and so we get a slight negative charge on the oxygen and slight positive charges on the hydrogen. That's super important, because when we're talking about water, this is really what we're getting into when we're talking about water. Life began in water. Okay, water has neutral buoyancy with organisms in water. A lot of organisms, not all, but a lot of organisms. It's the single most important molecule on Earth. I ask students every semester, what happens if you don't drink water? And almost immediately the answer is death. Okay, pause. Death is not the first step of not drinking water, but you're going to get dehydrated. Your lips will get chapped. Your brain will start to slow down. You will get unable to sweat effectively. Your kidneys won't be able to filter your blood effectively. You won't urinate. And generally speaking, humans need water. If you don't have water for 3 days, you have a high chance of death. So when we talk about water being so important, it's the main component of your body, okay, 70 to 90% water, but it also has unique properties because of the chemical charges that exist that makes water so unique on this planet. So we're going to talk about the importance of water and then the properties of water that make it really important on this planet. Okay, so again with the structure, let's talk about this again. When we look at water, remember, polar covalent bonds are charged because we are sharing electrons unequally. So if we look here, remember, hydrogens are 1 on the table of elements and oxygen is 8. That means that these electrons are going to be hanging out closer to the oxygen. If I were to look for that electron somewhere in this chemical bond where it's being shared unequally. That means that my oxygen ends up being slightly negative because it's pulling 2 more electrons towards its nucleus. And so it's got 8 protons in its nucleus, and then now it has basically 10 electrons on its outside shells. That means it has a slight negative charge, and then those hydrogens are slightly positive. In a single water molecule, that's really cool. But what happens, okay, 1, do you think any of your glasses of water have a single water molecule? I'm going to go with no. millions of water molecules. So what happens when we put a bunch of waters together? Well, all of these hydrogens are slightly positive, and all of these oxygens are slightly negative. And when things have charges, they are attracted to one another. So what ends up happening is when we have a polar covalent bond between one oxygen and two hydrogens, we are going to find that this slightly negative oxygen here is going to be attracted to the slightly positive hydrogen of a different water molecule. And they form these dotted lines called hydrogen bonds. Hydrogen bonds are really weak connections. They're going to break and reform very quickly and very easily when water is in its liquid state. So it's going to constantly be kind of like letting go and holding on, letting go and holding on. But the hydrogens themselves are staying connected to their oxygen. So you're basically taking these water molecules and they're kind of just moving across each other, okay? That is huge, because what that means is that water is able to stay in that liquid state, but water can also freeze, and water can also become steam or vapor. And we can do that by changing how these hydrogen bonds interact with one another, okay? So when we talk about the properties of water in biology, we're not talking about the states of matter necessarily, where it's ice or it's a vapor or it's a liquid. What we're really talking about is how it plays a role in biological systems, whether in whole ecosystems or in human bodies or animal bodies or plant bodies or whoever, okay? So there are going to be 6 main biological properties of water, and for the most part, they are reliant on the hydrogen bonds that form as a result of the polar covalent bonds that form between an oxygen and 2 hydrogens. The only one that isn't directly going to be related to that is your solvency, kind of. Okay, so let's talk about it. Solvency is going to be due a lot because of the polarity of water. Because those oxygens are slightly negative and the hydrogens are slightly positive, if you put a molecule that is either ionic or polar covalent, it has a charge. The water is going to interact with the charges of the other molecule. Now, because most of those molecules are going to have a charge because they gave up electrons, that's going to be really cool. That's how we can form salt water, right? The sodium and the chloride gave up or received the electrons, which changed them into that ionic state. When you put salt in water, there's a lot more water molecules, because water molecules are very small, and you're going to see the water surrounding the sodium or surrounding the chloride and breaking them apart into their component pieces, okay? In addition, though, we're going to find that water is going to respond to different substances in different ways. There are 2 things that we see. Molecules can either be attracted to water, meaning they are they are polar or ionic molecules, or they can be not attracted to water, meaning they are nonpolar. Hydrophilic is the word for water loving. So if you spill water on a cotton shirt, the cotton is going to absorb the water. Cotton is not going to be repelling water. But if you're wearing a raincoat or you have an umbrella, that is usually coated in a sort of oil, and that's going to be coated in a non-polar like wax or oil that makes that substance hydrophobic, where water cannot get into it and be dissolved in it. The water can't be absorbed into it. Water is not interacting with that molecule at all. Okay, this is often in relationship to the polarity of water and water having that polar covalent bond, okay, between 2 hydrogens and 1 oxygen. When we start then looking at how that ends up playing a role in other biological systems, we're going to see things like cohesion and adhesion. This is directly related to water's ability to form hydrogen bonds. Hydrogen bonds basically mean that water molecules really like to stick together, okay? So, your blood moves through your body with hydrogen bonds. It's just the coolest thing ever. Basically, what that means is your blood is adhering to your veins and cohering or having cohesion to itself. And that's the same thing with trees. If you've ever seen a tree and been like, how does that tree get water from the roots all the way up to the leaves at the tippy top? Well, it's like a big straw. Okay, and in that straw, the water is kind of just being pulled along. Those hydrogen bonds are holding on to one another, and the water is just moving up through that big straw. Okay, another example of cohesion, remember co meaning same or together, is where you'll pour water into a cup and the water will stick in little droplets, or it'll stick a little bit on the top level there. Or adhesion, when you actually have water sticking on the inside of a water bottle. You're going to see adhesion and cohesion all of the time, okay? Adhesion and cohesion are probably the easiest for people to understand because the hydrogen bonds are either connecting to a new substance through adhesion or sticking to one another through cohesion, okay? Again, this is really key, right? Plants wouldn't live on this planet and wouldn't get as tall as they are, and we'll learn a little bit more about that in diversity of life, if we didn't have adhesion and cohesion of water that allowed the water to move through the plant effectively. Now, when we talk about surface tension, okay, I love these little bugs growing up. We always called them water bugs or skaters or water striders, but we always called them water bugs. And then I moved to North Carolina. And water bug means something different. But when you see an insect sitting on the surface of a water or a leaf or something else, okay, what ends up happening is the water sticks more tightly to itself through the hydrogen bonding, and so that water strider isn't actually breaking the surface level. There's cohesion and adhesion that is making that water stick more closely to itself at the surface. In addition, these little insects, they're light, but big boats aren't, and big boats use the surface tension of water in order to stay afloat. In addition, these bugs have little non-polar waxes on their feet that repel the water. That is how they are able to stay even more above that, okay? But when we're talking about surface tension, it's why water doesn't spill if you fill your cup a little too full and you stop. It'll just sit at the top of that surface because water is sticking more tightly to itself than anything else. And that is because of those hydrogen bonds that form between the water molecules and the attractions that exist there, okay? We also have heat capacity and high heat vaporization. Again, really important. Water temperature rises and falls slowly. This is huge, okay? Because if you go to the ocean right now, I'm recording this in August 2025 when we've had the most ridiculous heat waves all summer, okay? I bet the ocean feels like bath water. I bet you it doesn't feel that great, but it took all summer to heat up, okay? It's now really warm. Or a pool. I haven't even gone to a pool because I can't imagine it's refreshing. You get in and it's like hot because the water is going to slowly absorb that heat and it's going to heat up and kind of maintain that temperature. But it doesn't do it overnight. It's not an immediate thing. Okay, that's why the watch pot doesn't boil, because it takes a lot of energy to break those hydrogen bonds fast enough that they cannot reform. So the water, when it's boiling and moving from that liquid state to that vapor state, the hydrogen bonds are being broken so fast that they can't reform. This is really important, though, to living organisms on this planet. If water temperatures rose and fell quickly, we wouldn't have life on this planet. Okay, you're mostly water. It's been 115 degrees outside. Okay, if you walked outside and water boiled at 100 degrees Fahrenheit, you would immediately die. Lakes would boil, the ocean would boil, we would be in deep, deep, deep trouble. So the fact that water is able to kind of like slowly accumulate heat, and water is actually able to release heat as it evaporates, is going to be really important to maintaining life in most living ecosystems, okay? And on the same side, it's not good if the water were to like cool down and freeze immediately. In the February 2025, we had big snowstorm. And one of the things that some of my students noticed is we were learning about this at roughly that time. They noticed that the ponds and things didn't really form ice immediately when we had that snowfall. By like the third day of that cold snap, then they were seeing ice forming on their ponds. And we talked about it, and it's because, again, water doesn't change temperature immediately. That water hadn't been freezing cold, and so it took several days of cold to like heat or to leach the heat out of the water so that the water was actually going to freeze, which is when the hydrogen bonds kind of get stuck and they stop breaking and reforming. They get stuck in a sort of solid state. And so that's going to be one of the things that we see, okay? Which brings me to varying density. So one of my favorite Magic School Bus episodes when I was a kid, because Magic School Bus was original when I was a kid, was when Ms. Frizzle took the students out to an igloo and was teaching them about ice and how water can act as an insulating blanket. And again, this is just so beautiful. One, this water sticks to itself, and we have adhesion and cohesion, and it allows water to move around our bodies and allows us to be able to live. And then we have it being able to resist temperature changes. And then even cooler, when water is no longer liquid and when it becomes a solid, it actually expands as it freezes as a result of those hydrogen bonds kind of getting pushed out and stabilized. And it means that ice floats rather than sinks. And this makes life possible in water. And as I had mentioned earlier, life began in water. So if we were to go and see ice sink to the bottom of the ocean or the bottom of a lake, when you dive into the deep end of a pool, the surface is going to be kind of warm because it's going to almost match the air temperature because it's absorbing that temperature through the day. But if you dive deep, and like I said, I'm not going in pools right now, but if I were to dive 14, 15 feet deep, the temperature doesn't really change. If ice sunk and deep water stayed cold, ice would never melt and life on this planet would not be possible. But what ends up happening instead is ice forms this thick, fluffy layer that ends up maintaining the water temperature or the ground temperature underneath it. So snow actually works as an insulator. And while a little bit of the ground might freeze, it's not going to be enough to stop life from living. Earthworms are still alive when it snows, okay? In addition, like my brother is a huge ice fisher. I'm from Wisconsin. He loves ice fishing. I always was like, man, it's kind of weird though. Like the ice is 3, 4, 5 feet deep and you're still getting fish. Right, because at that 3, 4, 5 feet deep, the temperature doesn't really change that much. And so the fish are still active. They don't care if it's light. They don't care what's going on in the terrestrial world. They're still moving around. They're doing their thing. And so you can still effectively catch fish even when it's under 5 feet of ice. And that's because ice acts as an insulator. It maintains that temperature in such a way that it allows life on this planet to flourish, okay? The last thing I do want to talk about briefly is the pH scale. And the pH scale is going to come up when we're talking about different labs or some different things. And one of the things to keep in mind is that while water is formed from oxygen and 2 hydrogens, and I said that it's a polar covalent bond and they're kind of holding on, that oxygen is much stronger than the hydrogens. And so occasionally the hydrogen will fall off of the oxygen, and so we end up with hydrogen ions, meaning hydrogens that are missing an electron. It's basically just a proton floating around, and then a hydroxide ion that has an oxygen, a hydrogen, and an extra electron. In a neutral pH, we see an equal amount of hydrogen ions and hydroxide ions. And so things like pure water, if we were to look at the numbers make sense for us to have just water is just pure water, okay? What's going to happen, though, is we can utilize hydrogen ions in various ways in our bodies, and we're going to talk about that with cellular respiration and photosynthesis. And then there's different reasons that we might want things to be acidic or to be basic. So, for instance, stomach acid is going to be acidic because it's going to help break down food so that we can get those covalent bonds and things broken apart so that we can reuse those carbons and hydrogens and oxygens in other things. We'll also see some things going, so baking soda and stomach antacids are going to be basic. So if you've ever had acid reflux and you take an antacid, what you're doing is you are adding a base to an acid to neutralize it. This is the same thing if you put baking soda and vinegar together. You're basically saying, okay, I am going to be replacing the missing hydroxides or hydrogen ions so that we can have an equal number and form water molecules. This becomes important when we talk about concentration gradients and some of the things a little later this semester, so please just keep that in mind, okay? Here is your check your understanding for the last part. Really big deal. Make sure you understand these hydrogen bonds for each of the water's properties. So, look at those sorts of things. Make sure that you understand these. You can give examples, and happy studying. Let me know if you have any questions.